Thanks very much. Good morning. We started to think about the ghost in the immune system, and I will explain why. So first, I will come to the background and the purpose of the modeling. So this is somehow referring to the question why these type of sandbox games in silico are useful. Then we'll come to the model and to some results with a specific focus on the lymph network topology and ending up with some conclusions. So what's the background? Radiation therapy is one of the three pillars of anti-cancer treatment. And there is more and more some evidence that radiation influences the immune response. So it seems that the immune system can be triggered by the effects of radiation. So if this is true, it would be really interesting to shape or to optimize radiation treatments to have more immune response. But for this, we need to understand what really happens. And the problem is that when we look to clinical trials, maybe that we can know somewhat, but it's hard to understand this. Specifically in a patient, we don't have access to the information needed to really understand the dynamics. And going to in vitro experiments, which are very controlled, this is not very helpful because there is no entire immune system. So we have to find a solution. So what we need is understanding the dynamics to have a chance to optimize such therapies. And the idea is that we go to models in silico and try to simulate scenarios and to look if we can find conditions which then may be given indication for designing new clinical trials. So to model such a system in silico, we need a tumor host ecosystem. This is not a rocket science. This is straightforward. There are well-known approaches to do ecosystem modeling. So that's not difficult. Even the radiation biological modeling can be implemented more or less easily. But looking to the immune system, this is much more difficult. You can think about the immune system as molecules and receptors. And you can try to model that. That would be the same as you want to understand functionality of Zoom by looking down to the electrons on the microprocessor. That's a relatively nonsense exercise. So instead of a molecular or mechanistic model, we tried to find a semantic approach. And the semantic approach for the adaptive immune system is that we consider this system as a trainable system. So I will show that we can model this by a perceptron. Related to this, we have research questions. For example, what are the essential components needed in such a model? Because the model should not be too complicated, but it should cover somehow the biological reality. So related to this, the sensitivity is interesting. So the question is, what is the sensitivity of the model regarding the model structure and the parameters? And looking to the model structure, the lymph node arrangement or the lymph network topology is an interesting aspect. Looking to the immune response, in principle, what we need is we need danger-associated patterns. So we have molecular patterns on the cell surface, and we must have a danger signal. So we are following here the danger hypothesis from polymatzing. Then we have the antigenic presenting cells, the APCs, which in principle detect molecular patterns, process them according to danger signals, and then prime T helper cells, and that at the end lead to a local T cell response. In a cascade of processes, then we have a more systemic response mediated by B cells and antibodies. But at the end, when we look to what this system semantically is doing, it's in principle recognizing, detecting molecular patterns and classifying them according to danger signal. And this classifying task can be modeled by a perceptron. So the idea behind is that information processing not only occurs in the neuronal system by nervous cells, but also may take place by a chemical system. Translated to the model, we have in blue the tumor host ecosystem with blue different tumor subclones. Here we have 9 of them. Then we have in green the host tissue cells, and in red we have the immune effector cells. So the part of the perceptron is motivated by the fact that we can implement a perceptron chemically. And this is a very important prerequisite to be able to implement such a system in a cell. So what we do in principle is we look for the danger signals, we look for the molecular patterns, and this then will lead to a perceptron response, which is responsible for producing the immune cells. Every immune cell has its specific antigenic pattern affinity. So that's shown here. This is that are the cell populations. And here you can see symbolized in these 3x3 matrices, these antigenic patterns with the different components. So we have here sort of immunogenic escape. So with more evolution, we have less antigenic patterns. And we have the host tissue. In this case, it's assumed that the host tissue pattern is orthogonal to the tumor patterns, but we also investigated non-orthogonal cases. How to get the danger signal? So we have viable cells, tumor cell population Ta-chi, and we have host tissue populations, and they will be irradiated, and by radiation, they will be damaged and transformed to pre-necrotic and pre-apoptotic cells. The apoptotic cells are not considered to activate the immune system in the same way as the necrotic cells. So there are different cell death mechanisms. The necrotic cells are assumed to strongly contribute to the danger signal. The presence of the necrotic cells is then used by this sigmoidal relationship to produce the danger signal, which then is used to train the perceptron waves. The antigenic patterns, in principle, are taken from the presence of the different types of cells. So this is the core of the model. Looking to the lymph network topology, you can see that the lymph nodes are connecting the blood circuit, which is a closed circuit, to the lymph vessel circuit, which is an open circuit. In principle, looking to the lymph circuit, it's a network, and you can see all these lymph nodes in this network. And it's clear that there can be different arrangement of lymph nodes, which are sensing the antigenic patterns in different regions. This led to 2 scenarios. In scenario 1, we have a tissue compartment 1 with a tumor and some host tissue, which is drained by lymph node 1. So we have APCs traveling from here to here, and here we have the priming of the effector cells. We have a tissue compartment 2, which is drained here by the lymph vessel compartment to the lymph node 2. This is a compartment which has mostly host tissue cells and only a few tumor cells, so it's considered as a compartment where we have metastasis. Please keep in mind that this vessel compartment is not really a compartment. There is a substructure, so that's not a homogeneous compartment. In scenario 2, we have only one tissue, we have only one lymph node, and both compartments, the tumor compartment 1 and the host tissue compartment 2, are drained by the lymph vessel compartment to the lymph node 2. Translating this to the model, we have in both scenarios, we have 2 compartments with the different cell populations, here symbolized by their antigenic patterns. But we have in scenario 2, in scenario 1, we have 2 perceptrons. So that are representing the 2 sites where the effector cells were primed, so the 2 lymph nodes. And we have 2 different subsets of immune cells, which then traveling via the bloodstream to the compartments. But there is a mix-up in the bloodstream. You mix up the cells. So there's an information exchange by the immune effector cells itself. In scenario 2, we have only one lymph node. So consequently, we have only one perceptron. So the information is mixed prior to priming the immune cells in the perceptron. And then we have a unique set of immune cells, which then go to the compartment. Every immune cell population is designed to act against an element of the antigenic pattern vector. Coming to the results, you can see on the left the tumor populations for compartment 1 and 2 here in brackets. These are the numbers in the brackets. Only compartment 1 is treated by radiation therapy with a standard fractionation of 32 fractions of 2 grays. In the upper row, you can see scenario 1. In the middle, there is a modified scenario 1 where no connection between the compartments is. So there is no mixing of effector cells. So that are completely separated responses. And in scenario 2, we have this single lymph node scenario. Looking at the results, we can see that in the completely decoupled case, we have here in red, we have the tumor cell population growing. So this is the tumor. Then you have the radiation therapy starting at day 570. And you can see how the tumor cells were killed. And in blue, you can see after a certain time how healthy tissue is recovering and repopulating the compartment 1. You can also see that in compartment 2, you have the growth of the metastasis. So you have the tumor cells here in green. And with this, you have competition to the host tissue. And this is the reason why the host tissue number decreases. And then we have an immune reaction. This is based on the tumor here coming. But also here you can see that host tissue relatively fastly is recovering. Looking to scenario 1, where we mix up the effector cells, you can see that this is not the case. We have no recovery of host tissue cells in compartment 1. We have only a few recovery in compartment 2. We have an immune reaction against the healthy tissue. And the same holds for scenario 2. So scenario 2 is not, and even scenario 1 are not favorable outcomes of the therapy. Looking to the perceptron weights, you can see why. So in the uncoupled case, you can see that the healthy tissue weights that are here, this is denoted by W2, all health tissue weights are even weights. So W2, 4, 6, and 8 are equal. That's a symmetric case due to the pattern symmetry. You can see that only in the middle scenario, we have these healthy tissue weights which go down to negative values, meaning that here the presence of healthy tissue in the second compartment leads to an immune response suppression. This is not the case in scenario 1, and it's less the case in scenario 2. You can see that the differentiation between tumor tissue and host tissue is smaller than in the uncoupled case. So what we know from clinical cases is that we can have an abscopal effect of tumor cells or of the immune system onto distant metastasis. That can happen. So you irradiate the tumor and you have an effect on distant metastasis. This sometimes is observed, but it's not observed that you irradiate the healthy tissue in the tumor compartment and then the immune system starts to fight again the whole healthy tissue. That's not observed. So that's not realistic. So what we can conclude at the end is, okay, lymph node arrangement. So the network topology is influencing the response. Okay, this is not a surprise. This we expected, and this is the reason why we did this study. But more presence of host tissue in the untreated compartment, where we have less danger signals, because we don't have radiation-induced cell killing, leads not automatically to an anti-host response suppression. And this is a surprise. This was not expected. So it seems that the complex mechanism of immunogenic cell death and elimination processes and the more complex signaling pathways with all the cytokines and all the co-receptors help the immune system to do the differentiation much better than in our model. So that means that our model, based on isolated perceptrons, trying to do the information processing only isolated in a lymph node, is not realistic. Maybe that we have to look for models which have more complex neural network-like structures. So there seems to be a more complex information processing, or let's say there seems to be more ghost in the immune system as we expected. So thanks for your attendance. There may be some questions from the audience, and thanks to all the collaborating partners here. Yes.